So I'm Matt Pyle. I'm an assistant professor at Berkeley. And I've been doing basically direct detector and dark matter throughout since grad school. I was at grad school at Stanford working on super CDMS. And now I'm at Berkeley, and I'm half super CDMS, half ultralight mass dark matter searches. Today I was going to split up my talk into two pieces. The first piece was just thinking about the design drivers for direct detection dark matter experiments. And I think this is one of those things that you should really think when you're trying to come up with a new experiment. Of course, like when you go to grad school and you have like, I'm going to go work in the LHC, the experiment's already there. And then you're just trying to figure out what your analysis is. But every once in a while, you get into this world where it's an exciting new world, right? And there's a new theory out there. And in this case, light mass dark matter is this area that's exploding right now. And so you really want to ask, if I could just start with a white blank sheet of paper, what would my detector look like? What is the best detector to search for this stuff? And so I think we're going to start with that idea of a blank sheet of paper. And we're going to go through and say, what would be the best detector to search for dark matter in all these different mass ranges? So that's basically the plan here. The theoretical overview is going to be crazy brief. It'll be one slide, because you've already had two talks on theoretical overview. And then we're just going to go through all of these different mass ranges and try to come up with theories of how to build a detector. I actually have plenty of time, so feel free to converse. We even have chalk on some chalkboards, so we can swap to a chalkboard whenever we want. So this is roughly the experimental world 10 years ago. All of us were searching for WIMPs, so things above 10 GeV and below a few TeV. And there was a few exceptions to this. A very tiny amount of money was going to ADMX for axions. But the vast majority of experimental physicists working in direct detection were searching for WIMPs. And it's a beautiful theory. We have this idea of the WIMP miracle, where there's new physics at standard model, which would exactly explain this relic density. And the problem is, unfortunately, we've been searching for this both at the LHC, and we've been searching for this with these amazing detectors that we're going to talk about actually in the next 10 slides, which are xenon and noble gas TPCs, and we haven't yet seen anything. So because of those two issues, we've really now started to push and say, this was a mistake to limit ourselves solely to this little region here. There's this vast region all the way down to 10 to the minus 22 eV in mass, where we could have ultra cold bosons, and then all the way up to 10 to the 48 GeV. And we really want to design experiments to search this entire range. And in particular, I actually tried to think about how to build experiments from 1 GeV down to something like 10 mil EV. That's the range where I try to play. You've actually already heard about a lot of these ideas. Asymmetric dark matter was just this last talk. Friesen was this last talk. And you can actually see all of these new ranges below the WIMP. So all of these areas here, as well as axion searches in this new community white paper that we wrote, which was US Cosmic Visions, which is, there's the archive number. So let's now go and first talk about design drivers for.
Question.
Yeah.
Why did you choose the minus 22 and 48? Why not higher or lower?
Oh, OK. So so minus 22 is basically the scale. I have these slides. It's a shame. Minus 22 is basically the scale of galaxies. So we know mass has to be there. 10 to the 48. Oh gosh, I don't think why that's set. Up here, this range is everything with like basically black holes and machos, like massive compact objects.
Probably gravitational lensing, like flickering.
Yeah, no. So that's what you. Yeah, so that's how you would search for those areas.
Okay.
Yeah. So I'm actually not going to go all the way up. I'm really going to talk. I'm going to start my design drivers at the WIMP scale, which let's say is below something like 10 TeV. So that's where we're going to start our design drivers. Wrong way. So let's go. OK, so for 10 GeV to 10 TeV, I skipped one slide. What's the first thing we have to recognize? And that is that we have really tiny rates, right? So when we look out at the galaxies, we know the mass density for dark matter. And then, if you say that dark matter has something like 10 or 100 or a TeV of mass, then you divide through and you get the number density. And basically, it's just this basic fact that, as mass gets bigger, the number density gets smaller. And now we have this interaction rate, which is going to be the cross-section times the number density times by the number of targets in your experiment. And that's going to be the reaction rate. So your cross-section is small because it's dark matter. We call it dark because it doesn't interact via all the forces we know. This is going to be tiny. If your number density is small, then your experiment has to be huge. So the very first thing we know is that the bigger in mass we go, the bigger your experiment has to be. And so if you're looking for stuff that's at 100 TeV or higher, when you go higher, you have to go to bigger and bigger experiments, right? So that's why IceCube is such a big thing if you want to look for super heavy dark matter, because you need it to be large. So so that's the first design driver that we know for dark matter experiments. OK, so the second one is we want to boost up. I have a delay here, which we're going to learn. There we are. OK, so the second one is we want to boost up that tiny rate. And we're going to use this idea of coherent elastic scattering. So we're going to scatter off of all the nucleons in a nucleus. And that means that the rate will scale as a squared. And so that means that the second design driver for high mass dark matter searches is a heavy nuclei. OK. So the third we have is backgrounds. So if we just go through the kinematics of this thing, we have some dark matter particle banging into a nucleus. It elastically scatters. We look at what is the recoil energy here. That characteristic recoil energy is going to be of 10 keV. And 10 keV is exactly the same recoil energy as like many radiogenic processes, Compton backgrounds, betas. So the third is going to be minimal radiogenic backgrounds. So how are we going to get rid of that? We're going to go underground. So if we have all these cosmic particles, all these high energy protons flying through, we're going to shield our detectors with soil. So we're going to toss, for example, LZ and Lux something like 5,000 feet below the surface. My experiment is at SNOWAB, and it is around 6,000 feet below ground. So that's how we're going to get rid of all of these cosmic backgrounds. And then secondly, we're only going to use radio pure materials and fabrication techniques. So here are people building Lux. And you can see the inside is built only out of copper and out of Teflon. These are materials that are known to be incredibly radio pure. OK. So even that won't be good enough because that rate is so tiny. And that rate's so tiny, again, because there's so few particles going through your detector, plus the sigma is small. So the final thing is we're going to have to, that background will still be measurable. So the idea is let's try to distinguish between that background and the signal we want to see. So the signal we want to see is this nuclear scatter. And all the backgrounds, the vast majority of that background, is actually electronic scatter. So a photon comes in, scatters off an electron, flies out, and the electron shoots out. So if we can distinguish between these two, then somehow we can also drop that background rate down. So here is, I think, truly the perfect detector for this mass range. And let's just go through why it's a perfect detector. So this is LZ, will be the next generation. But equivalently, there's 3 different collaborations, really, that are trying to build large xenon TPCs. And so what is a xenon TPC? It's just a huge vat of xenon. So, and by huge, I mean it has 7 tons, right? So it's massive. So you check out the exposure. You can get many years. You have many nuclei. Secondly, it's high A. It's xenon. Third, we're going to put this underground. And xenon itself is self-shielding. So xenon is a noble gas. So noble gases, of course, are noble. They don't interact with anything. And that's this amazing advantage, right? So that means that they don't pick up other materials. They don't pick up uranium and thorium very easily. And you can also distill them incredibly easily, right? So I can just go sit at the liquid point and I can distill them. I can boil them off and then collect what's boiling and leave behind what's left over. And I can make them ultra pure. So they themselves are ultra pure, so that means I can use them as a shield from outside photons. So if I have some, I don't know, in my material, or let's say I have concrete outside of my experiment, and it has some uranium in it, it shoots off a photon, that photon gets in. We can have it interact first with this outer layer of xenon, so we'll never get to this inner fiducial volume where we're going to look for our signal. So we're going to self-shield our experiment and protect ourselves from stuff that's outside that produces radiogenic events with xenon itself. So it self-shields. And then finally, it has electron recoil, nuclear recoil discrimination. And the idea there is we measure 2 different signals. So when this particle comes and interacts, it does 2 things. So first, it immediately produces some scintillation photons. And those bounce around, and they eventually end up in either the top or bottom PMT sensors. Almost all of them actually end up in the bottom, in the S1. So secondly, it produces some ionization. And if you put a huge E field across this system, then those electrons are going to drift. And they're going to drift up to where they get to right here. And in this region, we're going to have a little bit of a gas gap. So we're going to have a centimeter or 2 of xenon gas with a high E field across it. And when that electron gets into the xenon gas, now it can accelerate very rapidly and get to very high kinetic energies. And then when it hits one of those xenon gas particles, it'll shoot off lots of scintillation. So you're taking the kinetic energy, and that kinetic energy of that particle, and you're converting it into scintillation right up here. So you're basically converting the number of electrons you see into scintillation, which is a second pulse. So you get these 2 different pulses. They're separated by time. So you can figure out exactly how much scintillation one produces and how much ionization one produces. And it turns out that electron recoils and nuclear recoils produce different ratios of those. And you can pick it out. So I think what we just saw was that it was amazing how perfectly this detector matched our design drivers. And you see that here. So over the last 20 years, we've been searching for WIMPs. And something like every 5 years, we get another factor of 10, which is an enormous amount of sensitivity boost. It really has been an exciting time. And we're about ready to get another one of those factors of many boost as we go from this range of Lux, Xenon, 1 ton, and Panda, and we bump up to LZ, which will be coming on in 2020. So we should see this factor of something like 20 to 40 improvement in sensitivity over now in the next 2 to 3 years. So the x-axis here is, I'm sorry, yeah, you can't see it because my slide's cut off. The x-axis is mass. So we have 1 to 1,000. So you see this works very well above this 10 GeV threshold. And so finally, a few more points. This yellow here is neutrinos from the sun. So, so we have neutrinos coming in, coherently scattering off of nuclei, the same nuclei. So it's a nuclear scatter. So it looks just like a dark matter scatter. And that's going to set the floor throughout this entire process. Up here, these are neutrinos created by the atmosphere. Here, this is boron-8, which are neutrinos from the sun in this range. So that sets the floor, basically, for these limits. Now, there are people who suggest that we can go below the floor using directionality. I won't talk about that today. That's definitely challenging. Here, let's concentrate just about getting this another 2 or 3 orders of magnitude from where we are today to this range here. And that's certainly accessible. Yeah.
So that floor is an experimental floor?
Yes. Yeah. Yeah. Below that, you have to somehow come up with a technique to separate nuclear scatters from dark matter, from nuclear scatters from neutrinos.
So WIMPs are not dead?
So WIMPs certainly are not dead.
Can you repeat the questions, because we can't.
Oh, yes. Yeah. So the question was, what sets this floor? And it's purely an experimental floor. We would love to keep on going down in mass. And, in some sense, xenon is just a big, giant vat. So with enough money, one could just make these things bigger and bigger in theory. So potentially that would be possible to just keep on going down. The problem is we have this fundamental neutrino background. And one has to come up with schemes to separate those two out. And you can't just use electron recoil, nuclear recoil rejection. And you can't shield them, because, of course, neutrinos go through everything. So that is a challenging region. But we still have this huge range of something like 3 orders of magnitude from where we are right now to this range here. So it's, yep.
I'd like just to make a remark. As you say, this is for spin-independent interactions.
Yeah.
The degree of degeneracy with neutrinos, of course, depends on the type of interactions of the dark matter. So this is for a spin-independent.
Sure.
But of course.
Sure. No, but you of course pay the vast.
You will have a background.
Yeah.
How difficult it would be depends on the type of interaction.
Yeah, no, and also, I mean, the reason why we go to spin independent in the first place is because we have this nice coherent rate enhancement, right? And so when you get away from spin independent, you go to spin dependent and other effects, you always pay a rate penalty that's pretty vast. And
for example, you could have something much more exotic than that. You could have a coupling through a dipole moment, for example. And then you will have partially you are coupled to the charge, partially you are coupled to the magnetic moment of the nucleus.
Yes.
The spectrum is different, looks different.
Yep.
So you don't have any longer degeneracies with some of these interactions. In any case, if you're not going to go there, then we can discuss.
Yeah. I'm not going there, but yeah, and I think all of those experiments are really getting challenging because you are going below 1 e to the minus 48, right? So but we can talk about that later. Okay, so now we're going to go down in mass, and we're going to look at that 10 GeV to 100 MeV, and at the same time, we're going to pick up, because the energy scales are similar for nuclear recoil scattering and for absorption. The same experiment can be used for 1 to 10 eV ultra-cold bosons, where we absorb onto the system. So in this range, let's think about what happens. So here are basically all of those current experiments that we make. And what we see here is that none of those experiments have any sensitivity to dark matter in this range. And we can just ask why. And the answer is it's pretty simple. We have this giant nucleus here, and we have this very tiny dark matter particle, which has much less mass than the nucleus. And it's elastic, so it's literally like throwing a bouncy ball against a wall. So the wall is much more massive than the bouncy ball, so you toss it against, and almost all the kinetic energy stays with the ball, and very little is transferred to the wall. to have maximum transfer, you want to have the masses exactly the same. So this mass will go in, hit this one, and it'll bounce off. So this kinematic mismatch between these, we can actually see what is the characteristic recoil energy scale for transfer. And that's delta E is just going to be the recoil energy of this nucleus will be approximately the momentum transferred between the two particles, so that's just delta P. And if the particle is going in this direction and it kicks backward in this direction, that's approximately just 2 times the original momentum of the dark matter. And then you have divided by 2mn. So what we see that the characteristic recoil energy scale goes as m squared of the dark matter. And so that means that as we drop down in magnitude, we go down in characteristic recoil energy scale by 2 orders of magnitude, right? So here we have like I don't know, a 1 GeV particle. This is a recoil energy scale. And that's giving you in germanium, it's giving you something like 100 EV of recoil energy. If I drop from 1 GeV down to 0.1 GeV, then, so 100 MeV, I lose a factor of 2 orders of magnitude, and I'm now at something like 10 mil EV. Yeah?
Don't you extend this somewhat by going to inelastic scattering?
I can, yeah. So we'll talk about that in a bit. The moral here is that for this range, really the dominant design driver is energy threshold. So this is in contrast to in the high mass range, where we found that the dominant design driver was really just, you needed to have a big thing, right? You needed to have a huge detector. Here you don't need to have that. The real key is you just need to have a really excellent energy threshold. And now we can play with 2 different nuclei. So here we have this Mn. So the kinematic mismatch, the bigger the nuclei, the bigger the kinematic mismatch. So we can sort of play back and forth with this. So we can play back and forth with that, and we can say that germanium has a bigger A squared, so a bigger coherent rate enhancement. But the kinematic mismatch is going to be much more vast. So you're going to have, if you have really small threshold requirements, you can have larger rates. And with helium, on the other hand, it's on the opposite end of the spectrum, right? So there your A is 4. So there you are going to have smaller rates because you don't have the coherent rate enhancement. That's here in blue. But your kinematic mismatch isn't as bad, so you're going to have higher kinetic energies. So that's sort of, you can play the rate enhancement versus the energy threshold back and forth. So everything else is easier, right? So here is that exact same idea of the rate that we had previously. And because it scales, so it's sigma, the cross-section, times the number density of dark matter times by the n exposure. And because this scales as the mass density divided by m, we see that the interaction rate scales as 1 over mdm. And you actually see that in this plot right here of all of our dark matter limits from, let's say, LZ and stuff. They have this 1 over m dependence that as long as you're still sensitive to all of the particles, all the interactions that are going, this has a 1 over m scale. So as we go lower, it gets easier for us to see things. So for a given size experiment. So that's awesome. Secondly, let's talk about backgrounds. So that third design driver that we had for LZ was backgrounds, right? We had to somehow minimize backgrounds. So let's think about how that happens here. So here, it's a little bit of a messy plot, but let's see what it means. So here is that Compton background rate. This is the electron recoil background rate right here. And it's something like at 0.1 DRU, so 0.1 event per keV per kilogram day for germanium. In a basically a pretty good cryostat that's been carefully done, but not extraordinarily so. And here then is this coherent neutrino scattering floor that we see This right here is our boron-8 floor from neutrinos from boron-8 in the sun. And you can see that to go from here to here, it's something like a factor of 40. So that means to do the ultimate experiment in this range from 100 MeV to 6 GeV dark matter, one just needs, if you use germanium, one just needs something like times 40 electron recoil, nuclear recoil discrimination. And in colors, by the way, here, these are just some spectrum for various WIMP masses, 0.2 through 4 GeV. And you can see that where this crossover occurs. Okay. So that means that roughly in that region, so let's just look. So right here, the cyan is where you actually see the crossover between the neutrino background from coherent neutrinos from the sun and the Comptons. So above this cyan, so above 0.5 GeV, you're basically going to need some amount of electron recoil, nuclear recoil discrimination to hit that floor, the neutrino floor. Below something like 500 MeV, you don't need any discrimination at all. You'll just hit the floor automatically. That's your fundamental background. Okay, so now we're going to do the exact same thing with helium. So we just talked about helium, and we said that helium has less coherent rate enhancement. So that means, but the backgrounds are roughly the same, because the Compton background just scales with the amount of electrons in your system. So the amount of electrons, the amount of protons in your system just scale with the mass, basically. So if I have a kilogram material, I have some number of electrons, if it's xenon or if it is helium. And actually, I have more in helium just because the proton-neutron ratio is slightly worse. So that means that what we see here is my signal is suppressed, but my background on a per kilogram basis is roughly the same. It's actually slightly better because there's no tritium backgrounds, there's no beta backgrounds in helium because we can make it so clean. It's a noble gas. But in helium, that signal suppression means that to hit the boron-8 floor, we're going to need a lot of electron recoil, nuclear recoil rejection. We're going to need something like times 5,000. So that's the trade-off in this range that we're going to have for an ultimate experiment. So for the ultimate experiment, we're going to have something like a nuclear recoil. If it's out of germanium or out of any kind of high-energy material, you're going to have a really low nuclear recoil energy threshold. But you won't need that much ER-NR discrimination. If it's out of helium, by contrast, you can have your energy threshold can be much higher, but you're going to need a lot more nuclear recoil, electron recoil discrimination. This is hand wavy for reasons we'll talk about in the next lecture. Yep.
So this is basically taking a Lux-style detector and just switching xenon for helium?
Yes. So. Oh yes. So the question is how one would do that. We're going to actually talk about exactly what this detector would look like in a little bit in the next talk. There's a few different theories. The first one is exactly what you just said, which is let's take Lux, swap it out for helium, and put a huge E field across. Turns out that's actually really challenging to do. And the reason why is because electrons have very poor mobility in helium. They basically glob on to a bunch of other heliums. So it's not an electron that flies across. It's like an electron with a bunch of heliums going with it across. So it's very challenging to do electron transport in helium. But there are other techniques which are going to be basically using rotons. And it'll look somewhat more like supercidium S is basically, but just with a liquid helium rather than a crystal. But that's roughly the scale. And this is what you need in those two. So here are some sensitivity estimates in this range. So you can see there's a lot of them. So one of the things is I just gave you the ultimate experiment, which needs to have this electron recoil and nuclear recoil discrimination. If you don't have the ultimate, you can say, I can still do way better than the current limits in this range. So here is news G. So news G is just a neon, a giant neon sphere with a huge E field, and you're looking for ionization of neon. So it's a single, it's only a single signal, just the ionization. And they believe that they can do many orders of magnitude better than current experiments. CREST here is a calorimeter that we'll talk about in depth in the next lecture. Super CDMS is my experiment, and it is funded, and it is these lines right here for our first generation, which does not have ER-NR discrimination. And then we have 2 other ideas, which we will talk about in the next lecture as well, liquid helium and color centers. So that's this range. Right now, none of them are really proposing an ultimate experiment that will hit this neutrino floor. But we should all be thinking about that for subsequent generations. So I want to talk a little bit about this idea that so far all the design drivers were based upon this idea of elastic nuclear recoil scatters. And the question is, why hold yourself just to simple elastic nuclear recoils? Why not go off shell? Why not make the interaction more complex? So here's a paper that actually talks about this. The idea is dark matter comes in, it hits the nucleus goes off, but rather than immediately being on shell and conserving energy momentum here, you instead don't conserve energy momentum. You pay a rate penalty, and you throw off a photon, and then you conserve momentum here in the entire system. So now it's sort of a 3-body process, right? You have a WIMP coming in, a nucleus coming in, and then coming out is the WIMP, the nucleus, and a photon. So the problem is you pay a rate penalty. And here actually is that rate penalty. It's something like, integrated over the system, it's something like 10 to the minus 6. So this works if you have a giant 10-ton of xenon like laying around. You would totally look for the signal because it allows you to extend your search down to something like 100 MeV. But on the other hand, this 10 to the minus 6 penalty is vast, right? Like, it means that 10 grams of germanium is 10 tons of xenon. And 10 tons of xenon is an experiment that requires an enormous number of people and $100 million. And a single 10-gram crystal with huge sensitivity could be done in the lab by one group. So we really should think about this idea of the rate penalty. And I guess I would argue that you shouldn't do it unless you must. So if you have that lying around, you should go down that path, and you should, of course, look at it to see if you can see it. But on the other hand, 10 to the minus 6 is a big rate penalty to pay. So we should be careful and not go off shell unless we have to. OK, so now we're going to go down further. And we're going to go from 100 MeV to 1 MeV. So, OK, so far here, let's see what we have here. So these are some in cyan and blue. These are little bands here of basically the recoil energies for elastic recoil scatters for helium and cyan. And what I've done is I've used V escape for our galaxy and V average for some dark matter halo. So that's what. So V escape would be the highest velocity we would expect in our galaxy, and this would be something like the average, just to set the scale of what kind of recoil energies we could see. And we see this m squared dependence, 1 over m squared. So as we go down in dark matter mass, the recoil energy for for elastic nuclear recoil scatters goes as 1 over m squared. By contrast, the kinetic energy in the detector in the dark matter particle just goes as 1 over m. So it's much less sharp. So what we can see in this range, so something like, so where does it get difficult for us to see any kind of, like let's say an ionization signal on helium? Well, our neon, that sets basically at 100 MeV. So the best detectors you could think of are going to have problems with ionization at something like the 100 MeV scale. And if you want to look at like nuclear recoils in terms of heat, as in germanium, that's going to be something like 1 EV of energy. So you're going to go below 1 EV of energy if you want to search for those signatures. And so the moral is maybe there's something else we can do. And the idea that was tossed out there by Reuven, I think I have the citation down here, unfortunately, which you can't see, but by Tomer Volansky and Reuven, Essig and their groups, was let's actually look for inelastic electron scatters. So an electron is just better band matched in this area, right? If you're looking for 1 MeV dark matter, an electron is a natural thing to look because it basically has 1 MeV of rest mass energy. So it's going to be kinematically matched very well. So that's a check. But actually, it's even better, right? So it turns out that if I think of like all my electrons are going to be like in a nucleus, a dark matter particle comes in, bangs up against a nucleus, it kicks out an electron. So we can always conserve energy momentum because this is, and we can think of it in a few ways, but really the best is the kinetic energy and momentum. The form momentum can be conserved. So here is a case where we see that. So here, this is actually a band diagram for germanium. So what we can do is we can actually just take a bunch of particles here, and we bring dark matter in, hit scatter off of it. It kicks an electron from the valence band up into the conduction band, and we can conserve form momentum. We conserve K and energy in that process. So the threshold of this process is going to be set by the band gap. So if we use germanium, has a band gap of something like 1 EV, then we could go down to something like 1 MeV. So we exactly see what sets this range over which we can look for inelastic electron scattering. And that's just this range below nuclear recoils and something like 1 EV for ionization, which is the lowest semiconductor we see. Of course, if we're using xenon, there the band gap is bigger. And so we're going to necessarily have a higher threshold. So let's actually see that here in this plot by Reuven and Tomer, in which we can actually see a few things. So here is that threshold idea. So this is, again, experimental cross-section. All of these are for 1 kilogram year of material. And this here is the germanium line. Here, this is xenon, argon, and helium. And what we see is that the semiconductor band gap allows us to go to much lower dark matter masses with inelastic electron recoils. So you get huge improvements in this range. But you also get a change here. So the lower the band gap, by far the bigger the scattering rate. And it's something like 10 to the 3,000. So something like a factor of 3,000 between germanium and xenon. So what does that tell you? Again, it just sets the scale of these, right? So 1 kilogram of germanium is worth 3 tons of xenon due to this fact. And if you're an experimentalist and you're saying, which way do I want to go? It's a lot easier to instrument 1 kilogram of germanium. So that's one of these things. So one of the design drivers we're going to think about in this range is we want to have very small band gaps. Okay. Here actually is the one experiment that's so far been done, and it's actually by a xenon experiment where they looked for single electron, 2 electron, 3 electron peaks, and we'll talk about this in depth as to why they got stuck here and why they couldn't go much further down. Because this is 10 kilograms of xenon. Why weren't they able to get into this range? Because this is just 1 kilogram year right there. So they were, over 3 orders of magnitude off the expected sensitivity of this device looking at this plot. Okay. So here are a bunch of different models. In every one of these models, in terms of sensitivity estimates, you see this same concept. You see that basically for
Question. So in the previous slide, when you were using the band gap of germanium, what is the natural background? Is it the thermal excitation of the electrons above Fermi level?
No. So we'll actually talk about these detector backgrounds. Oh, yes. Again, yeah. So the question was, what are the backgrounds for these signatures? So we just talked about the fact that the radiogenic backgrounds weren't that big of a deal, right? As we go lower in mass, the radiogenic backgrounds are just not as big of a problem. And that's because the radiogenic backgrounds scale, Comptons are basically uniform from 0 to 200 keV. So the overlap of that with your signal is big when you're looking at signals that are 10 keV. But when your signal is just in EV, 10 EV, then the overlap with that big Compton spectrum is very tiny. So you're just not seeing the overlap. So the actual background in these experiments is going to be detector physics. It's going to be dark counts. So we'll see that in 2 slides. Okay, so a bunch of models. And here is the slide let's talk about. So here is actually basically that detector. So this is a xenon TPC. And here is a plot of Zeppelin 3. So it was one of the xenon TPCs. And this is the rate of single electrons that are being read out by the experiment. So they had single electron sensitivity. Here's 1 electron, here's 2 electrons, here's 3 electrons. And this is their rate of single electrons. It was 5.7 hertz. So they had a huge background of single electron events. That's going to make it really challenging to see a dark matter signal. And this is not fundamental. This isn't particles banging your detector. This is something happening intrinsically in the detector. So let's actually ask what it is we believe is happening here. So a few things could happen. Remember, we have this very high E field in this TPC, right? So we're charged at something like a kilovolt per centimeter. E fields are what we're putting on here. So maybe we just have tunneling of an electron off of the metal grid. So we have a huge E field. An electron can tunnel off the electron grid and fly across. So that's one possibility. Another possibility is that we had this interface between xenon gas and xenon liquid. And maybe electrons are getting stuck at that interface. And they're just sitting there. And we know actually some of them are because they believe that something like only 2/3 of the electrons are actually getting across into the gas. So 1/3 of your electrons are getting stuck right at that interface. And maybe those electrons then also tunnel out and then kick up and give you a single electron signal. So these are all single electron signals which aren't fundamental. They're not particles hitting. They're just your detector yourself is giving you this fundamental background. And this is not just seen in this detector. This is also seen in PMTs, right? So if you guys have ever used photomultipliers, you know photomultipliers have dark count rates. And again, why does a photomultiplier have a dark count rate? It's a non-equilibrium process, right? You have this huge E field to generate your amplification. And that huge E field will give you some tunneling. And so this is one of the problems, is that all of these experiments that are going to look for single electron and 2 electron and 3 electron signals are going to have to worry about these detector backgrounds. And that is what dominated Xenon 10. It wasn't radiogenic backgrounds. It was totally detector backgrounds. So I want to talk a little bit more about that, in which, well, in both of those 2 scenarios I just gave you, right? You had a single electron tunneled out of the metal surface. You had a single electron tunneling off of the gas electron interface. So you're like, that's going to hurt my single electron band, but my 2 electron hole region of interest, my signal, that should still be OK. So if the dark matter particle comes in and gives me 2 electron event gives me an event that produces 2 electrons, I should be able to distinguish that from all the dark counts. So maybe the dark count rate will only kill my 1 electron bin, but not my 2.
No, because you said the frequency is crazy, right?
Well, but at 5.7 hertz, let's actually just go through the math. I have the math right here. So let's just toss the math down at 10 hertz. So it turns out that a xenon TPC, I don't know if you guys know PMTs well, but a PMT has roughly 100 nanoseconds resolution. You can get better PMTs that faster, but the standard PMTs that all the xenon TPCs use are something like 100 nanoseconds. So that means, let's just say, what are the odds if your rate is 10 hertz? What are the odds that 2 events are going to actually come within the timing resolution of your detector if it's Poissonian? So by Poissonian, I mean that the events are randomly distributed in time. So I have some dark count here, and then suddenly here I have 2 that are within 100 nanoseconds of each other. So what are the odds of that? Well, I can just do that math. I don't even have to go through the Poissonian statistics. I can say, on average, if particles come in every 10 hertz, and I have 100 nanoseconds resolution, this is like 0.1 hertz. So a particle comes every 0.1 hertz, 100 nanoseconds. That's 1 e to the minus 7. That's 1 e to the minus 6. So of every 1 million leakage currents, I would expect 2 of them to be so close together that I couldn't distinguish them from one event. And if that was the only background Xenon 10 had, it would be great. Like, they could say, I'm not going to look at the 1 electron signal. I'm going to look only at the 2 and 3. I'm still going to have a world-leading experiment. And they're going to have soon 7 tons of material. So you can do really, really well just looking at the 2 electron bin. So the problem is we have a non-Poissonian leakage. So what they see is they see that the number of 2 electron and 3 electron events are way bigger than what one would expect from Poissonian leakage. And this is a problem. So let's think about how we could get this. And there's a bunch of R&D going on at Lawrence Livermore right now for this. Also, Peter Sorensen at LBL is playing around with this a lot, trying to figure out what's happening and why they're getting these non-Poissonian leakages. But the basic idea is here. So let's say let's start out with a process where I have a single electron tunnel out of here, flies across, kicks up here. It makes a bunch of UV photons, right? That's how we're reading it out. Some of those UV photons are going to get back into the xenon, and then they're going to be able to ionize an impurity. So we have a few impurities. We have an oxygen atom. We have something that's sitting in here. It has an electron sitting on it. That UV light ionizes that impurity. That impurity then has an electron that flies across, and it gives me another event. So things like this are ways that you can go non-Poissonian, and you can have a huge number of events start occurring very, very quickly. And you can start to get this non-Poissonian background. And so you have to somehow stop that chain.
So what impurities are you talking about? What kind of impurities you have in zinc?
You have lots of, you have some oxygen. You have just lots of stuff that's getting in there. I know oxygen is one of the big ones, but it's hard to keep things out of,
At what level are we talking about?
We're talking about very, very small levels. Like, I must say, I'm not a xenon physicist, so I can't actually give you exactly a number, but there's enough that there are impurities in there, and we know this because it takes them, for example, a while to purify their xenon, right? So it takes months for them to purify the xenon so that they can just get a drifting length of what they need, which is the interaction chamber. So xenon, the next generation xenon TPCs are about this big or so. They're about 1 meter in size. And they have to recirculate and constantly repurify the xenon for something like a month before they can make electron travel across. So that right there sort of sets the scale that before cleaning for a month, you need that electron which is drifting across will interact with an impurity in its little range.
They have cleaned for a month or more, right?
Yeah, so I think that's.
The names I thought was really, I have no idea, but very small, very pure.
Clearly, it's giving them a background. And I mean, you need something like that. You need some interaction, which will give you this secondary process. Because if not, it would work great. Like Xenon 10 has some kind of non-Poissonian leakage event. It's not just two electrons piling up on top of each other.
Do you know for argon too?
I must say I do not know this for argon. I will say that argon is a little more painful in that the rate penalty you pay, we talked about band gaps. So you are always paying this rate penalty, and argon has a bigger band gap than xenon. So you pay a rate penalty already for argon that's bigger than the one you pay for xenon by a little bit. But I don't know about leakage currents in argon, I must admit. Yeah.
Couldn't you test this by running the experiment with the dirty xenon and just seeing are there tons more events than when it's like ultra pure?
Yes. So they definitely are. Oh, yes, sure. Okay, so the question is what are the experimental tricks you could figure out to figure out where these non-Poissonian leakage events are coming from? And one answer was run it dirty, so leave some impurities. So I must say I haven't seen this one done, but it's a good idea. What I have seen done is, let's see, so there is some discussion on if it's caused by Teflon. So another hypothesis is that it's Teflon, and Teflon is basically a glass. It's this really messy molecular thing, and maybe it's storing energy and it de-excites, and it'll shoot off a UV photon every now and then. So this is actually seen as well. We know that Teflon has some, is definitely giving you some scintillation. But still you need that scintillation then to come and give you an ionization. So maybe that's another scenario. So I think people are planning on running without Teflon on the sidewalls. But then, of course, you lose your S1 signal. But you could just do a small experiment that was a xenon TPC. It is definitely an area of intense R&D. So it's not known as to what's actually the cause as of right now. But it's almost certainly at some scale, it has to be some kind of impurity states or something like that. OK. Yeah.
So actually, you said the timing resolution for the PMT is about 100 nanoseconds. And if the second electron is caused by the UV ionization, is 100 nanosecond enough for the electron to drift out to the gas?
Yeah, no, the drift time is a few microseconds. So yeah, depending on exactly where that occurs, you may still be able to tag many of them.
I see, but in that case, wouldn't there be a time correlation between the first event and the second event?
Yeah. So then only a certain percentage of them would pass your. Yeah. So there, there would be a time correlation, and the question is where in your xenon. If it occurs very near the top, then you can't distinguish. If it occurs down here, you could. So it's all about what that timing cut is. And yeah, so some fraction would be passed through, but the fraction wouldn't be that 1 e to the minus 6 fraction, right? That 1 e to the minus 6 was set by us saying we had a 10 hertz background of single electrons with 100 nanosecond resolution. 1 e to the minus 6 of them would give us leakage. If we had, with this process, the one comes in, it gives us a second electron, I don't know, 10% of the time it gives you a second electron somewhere in the bulk. Then you ask, if the bulk drifting distance is 10 microseconds, then 1/100th of them will pass your cut, and you're still playing the game, and you get hit again, right? So we really want to stop these multiplicative factors, and we really need to get rid of this non-Poissonian leakage. So this happens also in biased semiconductors. If we put an E field across a biased semiconductor, you get charge leakage. So this isn't just TPCs. Any time, basically, you put an E field across a system, you're putting it in a non-equilibrium state. So you're going to have some kind of tunneling rates. Like they want to be there. And the key is you need to have precision engineering. So I'll talk about my experiment in the next talk. In this talk, we'll talk about one place we have precision engineering, and that's in silicon CCDs. We've spent many billions of dollars, probably DARPA, in developing this semiconductor technology. And so a silicon CCD is basically just, again, dark matter comes in, hits an electron, puts it up in the conduction band. The electron flies across, the hole flies across, and then we measure the ionization produced with a CCD. So Sensei, which is basically the R&D arm of DOMIC, has actually just shown CCDs with single electron hole sensitivity, shown here. So this is an event with 1,550 electron charges. Here's one with 1,551.
Not everybody knows what DOMIC is, so why don't you say what?
Oh, okay. So DOMIC, so DOMIC and Sensei are an experiment that use CCDs to search for electron recoil dark matter. So now we've just talked about this idea of charge leakage, and so what is the charge leakage rate that DOMIC sees? So they've only set an upper limit. It's 10 to the minus 3 electrons per day per pixel. And if you put that through, the problem is that's pretty small. The pixels are pretty small, but that's a pretty small number, and you're like, score. The problem, unfortunately, is that the readout time takes 3 hours. So with xenon, we were talking about 100 nanosecond timing sensitivity. With DOMIC and Sensei, we're talking about 3-hour timing sensitivity. So you really have to ask the question, what are the odds of getting 2 single electron leakage events within a pixel in 3 hours? So that's your Poissonian rate. Yeah. So do you guys know how CCDs work? Well, OK. So CCDs are just little ionization detectors. And then, so you produce, it has a pixel. You produce, let's say, 1 electron hole pair, and an electron gets stuck here. So you have, let's say, 10 to the 6 of those pixels in an array. And the pixel has pretty huge capacitance, charge capacitance. It's a big thing. Charge capacitance scales with area. So you're like, uh-oh. So what you do is you actually transfer that energy from here to a small measuring device that has an incredibly small capacitance. And that's how you get the sensitivity. So you actually transfer this one single pixel to a sensing pixel, which has excellent sensitivity. It actually is even worse than that. It turns out that that sensing pixel still has 1 over F noise. All of electronics always have 1 over F noise. And therefore, they actually transfer it over and take it off and put it over and take it off multiple times to get to this single electron sensitivity.
1 over frequency? What is 1 over F?
So 1 over F noise is just a lot of it. It comes from many, many different physical sources, but it's a noise which gets bigger the lower in frequency you go. So that's why this is a DC measurement. So you can't just let it sit there. In some sense, if you let it sit there and you measure 1,000 times, you would say, oh, I would improve my sensitivity significantly. Because of 1 over F noise, it doesn't. Your DC noise is actually very, very big. So you have to somehow break that. So the way DOMIC and Sensei have broken this is they actually take it on and off. So your DC noise randomizes every time you take it on and off. And then they can do this square root n statistics. It's a very nice measurement. This is very, CCDs don't usually have 0.0, I think it's 0.07 electron hole sensitivity, right? This is a very beautiful device. And it requires a special readout. But that readout takes lots of time. You have 10 to the 6 pixels. You have to read everyone out by this little sensing pixel. And to do it, you have to read it out like 30 times, and you kick it back and forth. And so that's why it's 3 hours. That's a bummer. But anyway, let's look at these Poissonian numbers. So they have not seen any evidence of a non-Poissonian tail. So unlike xenon TPCs, they don't have this non-Poissonian tail. And here are the leakage events that they would see in a 100-gram-year exposure. Their single electron bin is just dead. It'd be 1 e to the 8. But their 2 and 3 electron bins are awesome, right? So here, their 2 electron bin is questionable, 2 to the 4, so they can't hit their backgrounds. But their 3 electron bin, that one actually has single electron sensitivity. So that would be the bin one would search and would give you the best dark matter sensitivity. Would be the 3, would be searching for dark matter which produce 3 electron hole pairs. And of course, this is only an upper limit on their pixel on their background. If it was lower, 10 to the minus 5, then you could also search in the 2. OK, I'll talk about my experiment, which also shows single electron hole sensitivity in the next talk. So far, OK, so here are the design drivers in this range. So you must have sensitivity to electron recoil, to single electron hole pairs, 2 electron hole pairs, 3 electron hole pairs. And the experiments that we've shown this are xenon TPCs, silicon CCDs, super CDMS so far. We need to have a very small dark count rate that's Poissonian and has no non-Poissonian component. By the way, PMTs have a horrible non-Poissonian component. Another way you could go is just have a really sensitive nuclear recoil detector. Again, the exposure is small, 1 kilogram year, not a big deal, to get really meaningful limits. So we're not talking about 10 tons. This is all you need is a kilogram. And the radioactivity limits are a DRU. So 1 event per keV per kilogram per year, per day is all you need. So it's, again, manageable in today's world. So now let's go the next step down, which is 3 keV to 1 MeV thermal relics to search for those, and to search for ultra-low bosons, which go from 10 millieV to 1 eV. Yeah.
We are ready.
Oh, we're already, OK, I'm sorry.
Almost.
OK, I'll finish quick. So the first step you could do is off-shell nuclear processes. Again, you pay that penalty, but you could go off-shell. So here is, so Catherine Zurich proposed this with helium. So you have a dark matter come in, hit a helium nucleus. You have an off-shell process, so you don't have to conserve momentum and energy. And you make 2 phonons back to back. So basically, 2 phonons back to back. Helium is really, really massive, and it is very, very slow compared to this dark matter. So if you want to conserve energy and momentum, you put the momentum of the 2 nuclei back to back. So you pay a penalty. Secondly, you could do inelastic electron recoils with superconducting band gaps. Basically the same concept as previously. The momentum energy conservation is not exactly the same as with electron recoils. But again, you can basically conserve for momentum. And the gap is small, so you're sensitive at very light mass dark matter. Here, the problem is energy sensitivity. You need to read out, you need to come up with a thing that will see quasi-particles at the, that'll see 1, 2, 3, 4 quasi-particles. So in terms of energy scale, that's 4 millieV. Finally, here's one that I really like. You could look for inelastic nuclear recoils with optical phonons. So here is another band. This is a band of the quantum vibrations, so the phonons in a system. And the energy scale here is 40 millieV. And you have an acoustic branch, and you have an optical branch. So why do we call these optical phonons? We call them optical phonons because they conserve form momentum very, very well with photons, right? So if you look at a crystal in the IR, it looks black. And why is it? Because you can conserve form momentum. So if I think of a photon coming in here, it's a very sharp line. And I have a photon of an IR energy. I can absorb it completely onto a longitudinal optical phonon. The same is true for very light mass dark matter. Here it's a parabola. But again, if I have a light mass dark matter with p squared over 2m right here, I can absorb, I can scatter off of it. I can take all of its energy and create an optical phonon. So here the design driver is a device that has single optical photon sensitivity. So here's a paper that we wrote on this. And you can see the sensitivity is incredibly enormous below this 1 MeV to create. So here we have a dark photon mediator where we have dark matter scattering via a dark photon, which was talked about in the slide before me. And this is such a great curve. And why is this curve down there so low? And that's only because of polar crystals. So when I think of a polar crystal, I have an ionic crystal, right? I have sodium. I have salt, which is sodium chloride. So I have a plus and a minus. These vibrations that we are seeing, these two branches, so the acoustic branch is when I have those two atoms moving up and down together, or moving to the right together. So that's the acoustic branch. All the atoms in a Berlin zone move together and are displaced together. The optical branch is when those atoms move against each other. So it's this moment or this moment. And if you think about what I have if I have a polar material, if I have a polar material and I have an optical phonon, I have a plus and a minus vibrating like this, right? So I'm changing the dipole, or if I have a dipole like this and I have it like this, it's going like this. So I am naturally coupling to the truest sense to that photon. I'm accelerating these particles around. I'm scattering very well. I'm absorbing very well because I have this perfect electromagnetic coupling. And that's why this is so strong. And that's why these limits here, for any kind of dark photon mediator, it's very hard to come up with another material that has this sensitivity because intrinsically it's so strongly coupled to a photon, which means it's so strongly coupled to a dark photon. So anything that goes through dark photons, this is a really nice technique to go for. So finally, the same thing works for ultra-cold boson absorption. Here is again, this is for a dark photon. You have this very nice sensitivity in a kilogram year. Way below, something like on average 10 to the minus 15. The limits are 10 to 10, 5 orders of magnitude better than what we currently have. So there are some backgrounds down here that break the rules, which is radioactivity. There's coherent photon scattering. And the moral is that you just have to put this in a photon veto, in an active photon veto. So here are the design drivers. In summary, we'll skip those. So our conclusions are, in every one of these ranges, we have different design drivers. As we go down in mass, our rates get bigger, so we don't need as much exposure. As we go down in mass, no matter what process we're looking at, the characteristics energy scales of what we're looking for become very, very tiny. So as we go down, we always have to get better and better sensors. There is one scale where this actually stops being true, and that's actually the 10 millieV scale. And below 10 millieV is here. Now you have so many particles in a single quantum state that the quantum density becomes greater than 1. And now you're not going to look for the annihilation of a single particle. You're going to look for the annihilation of like hundreds of particles. And this is what a radio does, right? Like when I listen to FM radio, I'm not trying to sense a single megahertz photon. I'm actually sensing a huge number of them, and a huge number of them hitting my detector. And that's what we're going to do when we go below something like 10 millieV, is we're going to try to interact with a huge number of them. So that's DM radio. We're going to build a radio. So every experiment below 10 millieV is just a radio experiment to first order. OK, thanks.
Any more questions? Time for a couple questions. Yeah.
Above like 10 to the 19th GeV where your scale cuts off, is there any realistic detector design, or is that just too big?
No, so all of those, and actually there's going to be a talk on this afternoon, right? About using weak lensing and stuff. So once you get to a certain size, you're not going to look for particles with, So what are we going to do? So we have 10 TeV, where it's going to keep on going, building bigger and bigger detectors. And like, IceCube is enormous, so you say, oh, I can go up to 100,000 TeV. But if you get up to that size, the odds of having a single particle just go through your detector become 0, right? So you're never going to build a terrestrial experiment to do that. But then there's some range where now we can start looking out in outer space and look for lensing off of these events. And that is basically what we're going to do for high masses.
All right, thank you, Matt. We'll